we start? Yeah, thanks for coming. So this week we have O-joung Kwon from Hanyang University, also member of Discrete math group, and we talk about another Erdős-Pósa property. Right.
Thank you. Yeah, thank you for inviting me. I'm happy to present my recent result about the Erdős-Pósa property of A passes with a certain constraint. This is joint work with Youngho Yoo from the Texas A&M University. Yeah. So we are generally interested in the packing and covering duality. So we have some set of graphs, and then given a graph, we want to know whether that either you can find the packing of k disjoint objects from the family, or you want to have some small set hitting or such as subgraphs. So this was fully motivated from the original Erdős-Pósa theorem. Maybe it's worth to state. So Erdős and Pósa proving that for every graph G and for every integer k, either G contains a k disjoint cycles, so in this talk, when I say it's disjoint, it's a vertex disjoint. Yeah. So for vertex set So from this result, many researchers have looked at another type of object and then see whether there is just some universal function like this. Yeah. Either you can find the packing of the k objects from another family, or you want to find some vertex set of some small size hitting all object. So this motivates a notion called the Erdős-Pósa property. Maybe I have to define that to easily communicate. So we say that the family of graphs has I will shortly call EP property. So if there is some function f such that, so for every graph G and for every integer k, G contains either k object from the f, k contains k disjoint. Or you can find the vertex set of size f of k hitting Does it make sense? So in this terminology, what we can simply say is that the set of cycle has an Erdős-Pósa property. Yeah. So this just says that the set of cycles has a property. Yeah. And then we want to know whether that another type of subgraphs graphs has the EP property or not. Yeah. So there are a lot of research about the modification of cycles, like odd cycles and even cycles, long cycles, and so on. But in this talk, we want to focus on the A passes, which is slightly different from the cycles. So I want to define what A pass is. So in picture, it's quite simple. So graph G, and you have some vertex at A, And A passes looks like this kind of path, where that its endpoints are in A and all other vertices are not in A. Yeah. So let me write it. So A path in G is a path. So, natural question is that is it true that A passes has the Erdős-Pósa property? So what I mean that is there some function f such that whenever you have a G and some A, so you can either find the K disjoint A passes, or you can hit the all A passes by some small number of vertices. So is there some universal function for that? So this is a theorem by Galai. That so A passes have EP property. I should say that so this function f is called usually called the gap function. So the natural question is that what about so A passes with some constraints. For example, we can think about A passes of length odd. Or even A passes, or another modularity constraint, or A passes something longer than some number. And so on. You can imagine the other types of A passes, and then we want to see whether that those objects have EP property or not. Yes. So there were two interesting results at the 2006 and 2010. Maybe I want to explain. Yeah. So people consider the two types of labeling. So in the title we have an undirected group labeled graph. So I want to explain the what unoriented group labeled. But before that, maybe I can explain what oriented group labeled. So that first, they gave a first general result. Yeah. So you have some group, and you have a graph G. So you have a undirected graph. And so for every edge UV, you consider the two orientation of this. So in the picture it looks like this. So UV and VU. So you consider the both. For every oriented edges, I want to assign some value, some element in the gamma. So let's say R UV is some element in gamma. But then R, V, comma, U should be a minus of this value. Yeah. And then we want to look at the path, A path especially. Now we want to, if we have some path, we want to read this path from the one end to the other end. It's like oriented way. Like you have a V1, V2, V3, etc. then we want to define RP as simply summation of R vi plus 1.
So you want to say abelian group or?
No. So here, so we really have a group, and then okay, yeah. So this is from the 1 to the last element. So we just add from the first element and second element. And so. But then, So maybe let me write that R31, V2 plus R32, V3, etc. And we define RP inverse as the reverse ordering of this sequence. Let's say the last is Vn, then maybe Rvn, Vn minus 1, etc. Then you can easily see that so RP is non-zero if and only if P inverse is also 0. So if you think about the specific values, then the two values might be different, but one is 0, the other is also 0. So that is to confirm. So we can simply say that some path is non-zero or not. So for these passes,
that they are just opposite of each other.
So R
I
of
think
P
so,
to the
yeah.
minus 1
Minus-
is minus R of P,
Right.
right?
yeah.
Does minus A mean inverse of A or?
Yes.
Yeah. So if this is considered an additive.
Right. So
So the group is on the underlying set of the group is just just on integers or numbers.
any.
So my notation, maybe if you like.
If you like that, then you have to replace plus by product, right?
Somebody decided to call these non-zero paths. And since then, everybody working on this is doomed because of this.
I see. Instead of non-identity.
Yes, exactly.
All right.
So Chudovsky, Gillan, Gerard, Godin, Lohmann proved that in this setting, non-zero passes have the Erdős-Pósa property. Still, gap function is type. So this gives us some corollary that odd A passes. So you can easily imagine that. So you take a group C2, and then every edges is assigned 1, and then every pass, the non-zero pass is simply odd A passes. Or, for instance, so you can imagine that in the outside you have some vertex at B. And then you are focusing on the A passes intersecting at least one element in B. Yeah, so A passes. Yeah, so this can be also formulated. The trick is that for every edge, so you consider the group C, and then so you sum out that every edge is linearly ordered like this, and then for every edge, so you consider to put the 2 to the generally 2 to the I, so that there is no cancel out, and then So every edge is not incident with B is 0, and then if edge is incident with B, then you give this value to them. Then non-zero paths should intersect at least one vertex. And also, this orientation is quite related to topological space. So it's related to fundamental group, and so you can formulate some passes on surfaces. I don't want to talk about in detail. If you want to look at the more, you can see the paper. But of course, in some sense, you may think about another type of group labeling, so-called unoriented group labeling. So that you can simply take a sum of the values, but now we consider the abelian group. Okay. So gamma is a sum abelian group. And then we consider some simply the edge to the some value, and then gamma p is simply in this setting. Slightly later, Paul Wallan have a theorem that in this setting, he considered the non-zero A passes and proved that they have a EP with gap function 50 to the k force, something like this. Not quite large, but yeah. Slightly worse than 2k minus 2. I'm not sure, yeah, it's tight. Maybe someone can try to optimize this.
Is there a lower one?
I don't know. Yeah.
Okay. I don't know.
Maybe
Okay,
2k.
yeah. I thought like some exponential. Not exponential.
Yeah. So this also gave a corollary to the order A passes, of course. But that is a better result. But also, you can think about another modularity, like a modulo 3 or something. So non-zero mod 3 or something like this, etc. Because you cannot really present this as here in a, I don't know, yeah, I think not possible, because you may have some cancelling out. So until we now we see the odd A passes. What about the even A passes, right? Yeah. So time flies, and then some people were interested in this question, especially Henning Brun and others have some issue.
Maybe I'm confused a little bit.
Yes.
That unoriented group labeling setting is satisfied just oriented group labeling setting maybe with gamma abelian group, so maybe satisfy the original gap function 2k minus 2, but I don't know why the unoriented case has much larger gap function. You're asking the difference between these two.
Yes. Difference between them. So when this is abelian, but so you have some different values for the orientations. Like this is, if this is a 3, then this should be minus 3. And then when you read in this direction, you have to add a 3. Yeah. It's slightly different. Yeah.
Ah, I see.
Sometimes you have to subtract if the order is different. Maybe you can play with some percentages. Yeah. So they proved that actually it's quite simple. So it has a EP with a 10K function, and they consider also long apices. So apices of length at least L as a EP with OKL. Even long, even apices also have a.
So this is without the labelings now?
Oh
This is
yeah,
just the
this
original
is just the user. Yeah. But they also found a simple example that the apices of length 0 modulo 6 do not have a Erdős-Pósa. Actually, this is generalized to the any 6 can be generalized to the any composite number larger than 4, and then actually 0 can be any value. But for 0 modulo 6, I would like to give an example for certifying this argument. Then you take some grid. And then you put the pendant vertices on the left and then right. So you, yeah, maybe you subdivide. So you, yeah, okay. So let's say, so this length is 1, and then on top, so each edge is subdivided so that the length is 3, and then this is the length 2. And all other edges are exactly 0 modulo 6. So you can you say that this length is 6 in every way. Then I take this degree 1 vertices as 8. So this together with this would be A. So what is apices of length 0 modulo 6? So it should start from the left, and then you either at least one edge on the above, and then should go out here.
Oh, only the top row has 3.
Yeah, only top row is 3. So other is 3. Yeah. So if you come back to here, then it's if you don't use these edges, then value will be 2 times the 3 carries. Couldn't be 0 modulo 6. And also if you go out and come back here, then it would be 1 plus 3k, right?
What is K?
I mean that you might use many edges of this. Yeah. So it depends.
So
Yeah.
the number of times you use in the first row.
Yes. So yeah, I just want to say that it's not possible to have a 0 modulo 6 if you go left and then right. But then, so the only way is that you start from the left and then you eat something on the top and then you go out, right? Then you cannot have a 2 vertex disjoint circle. Do such things. Right? If you once you have this, then you cannot go above and then come back here. But then, if you want to kill the all such passes, you actually kill the majority part of the grid. Yeah. So which you cannot give a universal bound. So if you give me any number, that I can increase this grid super large, so that you cannot hit using that bound. Yeah.
Max says.
Yep.
So for the remaining numbers that are not composites, do they have apex? Do they have Erdős-Pósa?
You mean
Yeah,
6 is prime.
Yeah. So that's the next.
So do they all obviously have half integral Erdős-Pósa?
Yes, that's my result. Yeah, so they remain some question about the 0 modulo 4, so they cannot resolve the 0 modulo 4, and then actually Hanyang also resolved that question. So he considered the length 0 modulo 4 EP, but this result already quite complicated in their proof. They use grid theorem and so on. Yeah. But maybe you can find a simpler proof, but at the moment this proof uses the grid theorem and like 10 pages or something like that. Yeah. 2 modular 4 also have EP, but they also argue that the 1 or 3 modular 4 do not have EP. Yeah. But then somehow the remaining question is that what about the 0 modular prime number? They only consider the composite number, and that was the result by Thomas and Youngho. Yeah. So they proved that the 0 modular prime P have a Erdős-Pósa property. Yeah. But actually, they give a more general result that for every they characterize for which so gamma and some specific value in gamma for which in the unoriented group labeling the A passes of weight L have EP property. Yeah. I will give you the characterization later. Yeah. So yes.
What is the order of the gap functions here?
For prime, I think they use a grid theorem. Yeah.
Okay.
So grid minor bound related.
So still
It's
polynomial.
Yeah, still polynomial. I believe. Yeah, I didn't check. Yeah. So our question was 2 things. So at the first question was that so I was interested in this question, and then what about the half integral? That was actually the first question, and then later I did many work with IBS people about the cycles with group labeling, and then we want to think about instead of some fixed value, we consider some subset of gamma, and then what about A passes of weight in the sub value? Okay. So maybe I write here. Yeah. So. Also, I want to ask about the half integral Erdős-Pósa property. Maybe I want to explain the definition. So, original Erdős-Pósa property says that either you can find the k disjoint subgraphs. So, k disjoint subgraphs means that you have a k subgraphs where every vertex should be in the at most one of the subgraphs. But maybe sometimes the Erdős-Pósa property doesn't hold. Then we want to relax this condition that maybe instead of this, so you want to have that k subgraphs in F where every vertex is involved in the at most 2 times. Then this condition is relaxed, so it's more possible that that may be true. Yeah. So this modified version is called the half integral Erdős-Pósa property. Yeah. So yeah. So I want to say that this was fully motivated from our previous result about the cycles. With Pascal and Kevin, Cage. Hanyang. And also we have some result for the cycles in the same similar topics. Yeah. So now I want to explain our result. Yeah. So we actually have a kind of answer to this, but for the finite groups, but we have some general result. So we say that lambda satisfy EP condition yeah, so if the two conditions are satisfied, so the first condition is that for every 3 values in gamma with whose summation is in lambda, then yeah, so one of 3 should hold. So either A plus B is in lambda, or 2A plus generated by C, the section lambda is non-empty, or 2A plus 2B plus 6. And second condition is that for every A, B, C in lambda, 2A, either 2A plus so 2A plus so these are two conditions, and yeah, our theorem is that if gamma is a finite abelian group, and lambda is some subset of gamma, and let's say the F is a basis of weight in lambda, then F always has the half integral Erdős-Pósa property. And second thing is that F has a Erdős-Pósa property if and only lambda satisfies EP condition.
So this is the only also necessary conditions. The others are also optional.
Sorry? Yes, yes. But we only able to prove for finite abelian group.
So this is it and only.
Yeah,
Yes, it was behind. Okay.
You can, I can explain the why they are a necessary condition. Suppose that EP1 doesn't hold, then you can easily create actually the similar example where so you have so you imagine the grid with these things, and then you put A on here and B on here and C on top. suppose that there exists ABC with A plus B plus C is in lambda, but nothing this happens. Like A plus B is not in lambda, so that means that you cannot just go like this to have a lambda value, or 2A plus sum of C is this value, so this should not be lambda, and the third thing is that this is not lambda. Yeah. So if P1 doesn't hold, then Erdős-Pósa should not hold. But second example is some slightly different, but also you have a grid where you put the A here, and on the top you put the B, C, or whatever, and then on the right hand side you put the B values. Yeah. Yeah. So then this is a. Yeah. So this is just
the vertical edges of B?
the right.
Yeah.
So the most right edges.
Okay.
Yes. Yeah. But then every A path should use 2A, right? So 2A plus B plus C is lambda. Then something this kind of thing is A path, the value. But the condition, if condition doesn't hold, then this means that if you just use like this, then this is not the value in lambda, and also this kind of thing is not the value in lambda. So, but interestingly, we proved also the opposite. So if you satisfy AP condition, then also has the Erdős-Pósa property.
Do you have some counterexample for infinite case?
Yeah, I will explain later. But so in our result for the cycles, so we also think about that the excluded value is the bounded, right? So if the excluded number is unbounded, we don't know about the cycles as well. So we also don't know about this. Yeah. So allowable value is, so if you take infinite group gamma, and then allowable value is finite. So this is finite, and this is infinite. I think even half integral Erdős-Pósa doesn't hold. Yeah. So we have some example for cycles. That is technical to explain. But if both is infinite, I think we don't have a characterization. This is one of open problem. I will explain later.
In this example, if you take multiple horizontal lines and vertical lines, then 2A plus the group generated by C plus the group generated by B,
Yeah.
does it count in the counterexample?
No, but yeah, suppose that there is some value ABC where this is true, but this is empty and this is empty. But we don't really consider the 2A plus 3B plus 5C. But once this is true, then you have some paths, right? Yeah. So this just guarantees that you cannot simply kill the all passes because there is at least one pass alone using one and one.
I don't have feeling about numbers, so that does condition, or how strong does condition it is? I mean, if we choose some random number and a random group, and is it likely to be satisfying that condition or not?
Yeah, okay. Yeah. Maybe we will see the corollary about the Thomas and Yu's characterization. If you see it, then you can have something. I will explain just. Yeah. Also, after we proved everything, so we ask whether then maybe EP1 whole implies EP2, etc. So it's very confusing to us, but we proved that at the end we proved that those conditions are independent. So, yeah. That is also proved in there. So maybe before saying some proof, I explain some corollaries. Yeah. So one corollary is the Thomas and Yu. Yeah. So they proved that the gamma is abelian group, and L is some fixed value, then so makes exactly L has if and only so either gamma is C2, okay, and L is 0, or gamma is and L is 0 or 2, or gamma is prime PC and any L. So of course, this is in terms of all abelian groups, not just finite abelian groups. But so one direction is easy, like if this is, so if the group is not, if the situation is not one of these, then it doesn't have an EP property, so it's the kind of observation. The main part was proving this direction, so this all of them are finite groups, so we can use our result. So you can see that the fraction is like this among the whole group of finite groups. Yeah. It's rarely happen somehow. Yeah. Also, so actually we try to push like so in this result we consider the infinite groups, and then we consider the some other types of product of groups. But their corollaries, also, some of the corollaries also can be captured by finite groups. I want to explain one thing that, you may consider that you have A, and then you have some set of edges, F1 and F2 and F3 and so on, right? And then you are asking, what about the A passes containing at least one of F1 and F2 and F3 and so on, right? So this could be easily translated using the product of three groups. If you have three sets, like if you have incident, so let's say F1 is a set of edges, and then if an edge is in F1, then you give a value 1, 0, 0, and 0, 1, and then you are saying that you want to have some non-zero coordinate on everywhere. Yeah. So that is my requirement. But this actually can be captured also by finite group by just C2 product, C2 product, C2. So you may be worried about the canceling out, but for every edge, for instance, edge is contained in the F1 intersection F2. Then the trick is that you just have some multiple edges like this, and then you put the value like 0, 0, 0, 1, 0, 0, and 0, 1, 0, and 1, 1, 0. Yeah. So simply to avoid the cancel out. Like if you once use at least one edge of F1, I can add one value there. And then later, if you use more F1 edges, then you just pick another thing to say that you don't have a cancel out in the first coordinate. Yeah. So you can simply say that lambda is just 1, 1, 1. Yeah. Also, if you want to say that you contains like 5 edges of F1, so you consider G6, and then so you up to 5 values you consider, and then later you just don't care about the cancel. So you take 0 value for the first coordinate.
If you want to say exactly 5 edges, then maybe it's difficult. Right?
Yeah, that will be difficult. That was also difficult in the infinite. Yeah. So another corollary is about the AB passes. So you may, so while you consider the A passes, you may consider the AB passes, right? Like Mengele theorem. so you have two sets A and B. So your edges are labeled by some gamma, and you are considering the A-B passes of weight in the lambda. So lambda is just a subset of gamma. Right? Actually, this can be captured by saying that you can extend by your gamma product G2, and then so you consider the A union B as one set. But while the edges instant with A, so you add in the second coordinates you put 0, 1, and then edges instant with this you put the coordinate 1, 0, and then you want to extend the lambda with so A, B, A, 1, 1, where A is in lambda.
So you want G2 times G2?
No, A is from the original gamma. Yeah. So you have this setting. You have a group, and then labeling with this, and then you want to see the A/B passes of value in lambda.
So G2 squared then, right?
G2 squared. Yes. Yes. But then in this figure, yeah. So value in here should be a pass of like this. And then you can argue, you can adapt our main theorem, but actually the corollary is very simple, that actually mostly it doesn't have Erdős-Pósa property. Yeah. So suppose that lambda is not the all set, so there should be some element not in lambda. And then you pick some C in gamma, so that the A plus C is in lambda. But then you could see that so you put the value A here, value C here, value C here. Yeah. And then from here to here, yeah, so you should use something like this.
So on top you put 0?
Yes, I think so. Because
so everything in the grid
okay.
is 0?
Okay, no. Yeah. Yes, actually, yeah. So it's easier to mention the like. Yeah. Sorry. Yeah. So. So I take this multiple labeling, that would be easier. Yeah, so 1, 0, and the top value would be 0, 01, and this value would be C, 0, 0. Yeah, and then lambda is 1,
But that's not the labeling for original labeling, right? It's extended labeling. So you're trying to prove that it's not Erdős-Pósa.
for the original group.
Yeah. Right.
I remember. I think you can translate it to the original. Yeah, maybe. Yeah, maybe you have to modify the. You have to put some value here. Maybe I will check later. Yeah. Yeah, I just like this. Yeah, I will check. Yeah, and then lambda. If lambda is gamma, then it just consider the all AB passes, so follows from Menger. Yeah, and lambda is empty. Is here. And one nice thing is that for EP, there are so mostly not Erdős-Pósa property, but for any lambda, so half integral taking half integral Erdős-Pósa property holds. Yes. For any finite abelian group, gamma and lambda, and so instead of looking just the AB passes, you might consider the weak version of AB passes, where that in the intermediate you might have some more A and B vertices. You can easily extend this result to this. Yeah. So recently, then Mike and Colin have some result about this. I should mention that. Yeah, what they prove is that they consider the oriented group labeling, and then consider the non-zero AB passes, and then they have a half integral Erdős-Pósa property.
You mean the weak?
Yeah, for weak AB
Ah.
passes. Correct. May I explain 2 minutes about the proof, maybe? Yeah, we actually describe all possible obstructions in some sense. Yeah. So obstruction looks like this. So you have A, and outside of A you have a grid. Yeah. So you might have some linkage Q1 and some linkage Q2, and then over the boundary of the grid, you might have some linkages like this and this, and yeah, so this, and maybe this kind of thing might happen like this. So this kind of linkage is either one of these things, and or nested one, and crossing ones like this. Yeah. So basically, we want to have this kind of obstruction, and you have some values G1 to the Gm, where you have linkages P1 to the Pm, and H1 and H2, such that each pass in the Pi has a value in Gi, and then Qi has a value H1 and Q2 has a value H2. And then somehow minimally generate the value in lambda. And then, so this is called lambda inlet subwall. And then our result is that so you can always find so it's like Bruce Reed's result. Like you can either find the K disjoint A passes in lambda, or you can have some heating set, or you have a lambda inlet subwall. So from this theorem, what it proves is that for half integral packing, it's easy because lambda inlet subwall always contains half integral packing. Yeah, I mean, so somehow you can mix one pass for each of them. But it's a half integral packing, so you can put a nice way to have a half integral packing. For Erdős-Pósa property, so we have some more argument that if you have an EP property, then some kind of conditions cannot happen, and then we say that in that configuration you can find actually K disjoint guys. Yeah, but very nice connection to the cycle is that we prove using the cycles actually. So what they do is that So you link nicely this Q1 and Q2. Yeah, we have two options. You can make linkage like this, so that this together is nested, or you can put edges like this, so that it's crossing. So we have two options, and then we can manage it that in certain condition, under certain condition, you can put either one of them, and then we find the k disjoint cycle here, which give k apexes. This is some nice connection to the cycles. Yeah. So maybe, so this is the main contents, and maybe I put some questions. Yeah, it's also question for the cycle result. Characterize lambda and for z, for which A passes. So far, we consider only the finite abelian groups. So what about the infinite group, right? For that, if maybe, so we have some result that if lambda is finite, then it doesn't have an Erdős-Pósa property. It should be infinite, actually. But there are so many infinite subsets, so we couldn't characterize all of them. Yeah. So this is one question. And another question is about the directed passes. So, for instance, what about the directed? For instance, all the A passes. Yeah. So they do not have a Erdős-Pósa property. Yeah, I'm interested in the half integral Erdős-Pósa property. So you can easily say that if you orient, so you take a grid and then you put the direction from the left to the right, and then you go up and down, something like this, and then everywhere is even, but here is only odd on the top. Then you should have some path like this. So direction already gives that you have to start from here and then end from here. So this certifies that you don't have an Erdős-Pósa property. But we are not sure about the half integral Erdős-Pósa property. Do they have a half integral Erdős-Pósa property? Yeah, it's interesting that usually that in the undirected case, if you have a bounded trees, then you are happy. But this graph is in the directed setting, the directed trees is large. Directed trees is small. So it's a cyclic graph. So maybe we may use another way. Maybe you can use some undirected trees and so on. Yeah, it's not clear. Maybe there are. So for directed, simply A passes. So they have a Erdős-Pósa property. This is a result by Krischer. In 2005. Yeah. Okay, so this is the end of my talk. Yes.
Did you use grid minor theorem in your proof?
Yes, maybe. Yes, a lot.
Then the
Yes.
gap would be the grid minor gap.
Yeah, we use a grid minor function. Yeah, basically that maybe I can give you the first step. Yeah. So what you use is that so you consider the small separation, and then if a small separation separating two A passes, then somehow we are happy because you can apply induction. Because this part has some apexes, whatever you want, and then you have apex. So here the maximum number should be one decrease by one, and then decrease by one. So you can apply the induction for each side, and then you just add this set to the. But then, so this means that whatever you take a small separation, the only one side have apex that I want. This give a tangle, and then you find the grid and you do something.
It's good to give a talk right after the winter school. I have a naive question, so that I mean, probably this should be obviously false. So if I'm interested in apex problem, what if I add a new vertex and make it complete to those vertices in A, and then think of the cycles using this my new vertex.
But if you want a vertex disjoint, then you can use only one.
That's right. Okay. Maybe you can just blow up, right?
Yeah, that's the original discussion. So later we found a way to link like this. But at the beginning we tried to put a click here or something like that.
Right.
Is the finding these kind of linkages some kind of Erdős-Pósa's lemma thing?
Yeah. So yeah. So we use a apex theorem by Porolla. Yeah, we care about the general group, right? So the procedure is like this. So suppose I have some one path which have one value L. So now we consider the subgroup generated by L. Then if this already intersect lambda, then we are happy. But if it doesn't intersect lambda, then we consider the quotient group. And then you apply the Porolla's result. At the beginning, you find the non-zero paths. So this gives us some non-zero A paths in a certain way. And then you use Erdős-Pósa to find the one.
Mostly curiosity, do you know if there are any results with when variables are in a semi-group instead? Probably not Erdős-Pósa, but maybe half integral?
I have to think about that. Yeah, I'm not sure that.
Like length at least L, anything of that? Because it's a very natural condition for a semi-group.
Perhaps, yeah, maybe some of the parts. Possible. But I'm not sure we use a quotient group a lot. I'm not sure
Okay.
the same group is very different over there.
Right, any other questions? So if not, let's thank the speaker.